Good evening, guys. Welcome to our first DSC event, an introductory session to 30 days of Google Cloud. This session will be an intro to cloud in general, and then we'll be talking more about the platform. This session will be split into two tracks. One will be the cloud track, and the other will be ML track. The cloud track will be handled by Pranav and Bhargav. The ML track will be handled by Sparsh. If you have any questions, you can ask them in the comment section. If we get the time, we'll answer them on the stream. If we don't get the chance, please ask them on the Slack channel so that we can answer them there. Pranav?
Yeah, okay. So, sup guys, this is Pranav here, and along with me are Bhargav and Sparsh. And today we shall be delivering a webinar on cloud. So the main goal or the motivation behind the session was that, when you're doing your quick labs, you find yourself in a situation where you're like, okay, fine, I'm following steps, I'm copy pasting these commands, but what am I actually doing and what is the actual purpose of this? So hopefully we should be, providing you some clarity on what cloud is and some of the core building blocks, as well as the purpose to what Quick Labs is trying to train you to do. So without further ado, I shall start. This is going to be an introductory session, detailing, all about cloud, the history, how it's useful, and the basic concepts that you should know about. So, okay, let's start. And immediately, let's start with a history lesson. All right. I mean, what webinar is complete without one? So, okay, it's 1940s. World War II is in full swing. I don't know why I said that, but anyway, cool. And the first data centers started appearing now. So these are mainly, those vacuum tubes, punch hole sort of computers back then, the mainframe ones. And these were meant for scientific research, and slowly it transitioned into what we see as the data processing industry. So 1960s to 80 was when this started picking up, and people started realizing there was actual money to be made in processing data. 1980 onwards saw the rise in grid computing, cluster computing, and peer-to-peer systems till about the late 2000s. And all these complicated words basically mean the same thing, that uh, you know it goes to the core of data centers, which is a lot of compute and storage located in one place. The late 2000s, however, saw the start of the behemoth cloud industry, with AWS being one of the first major players in the scene. So that's how the black and white one is how it used to look. This scary monolithic creature on the this bottom corner of the screen is how it looks today. Okay, so cloud today and how it impacts us as a society. So, cloud today is present in mainly three forms. So, you have public clouds such as GCP, AWS, Azure, and many, many more. DigitalOcean has many good offers coming in. So, these guys rent out the services. It's not necessarily just virtual machines, right? It can be hosting an app, or like Firebase, or there's so much more according to what they provide. Okay, then you have the next option of private cloud. So this is when large companies with a lot of money invest in their own cloud infrastructure, where they can use this for their own computation tasks. So if you rent out, in the long term, it's going to be more expensive than actually building your own system. So large companies tend to go for their own solution, and also this allows them to have control over their own data. Now, hybrid cloud is a mix of both. It's public cloud plus private cloud. So it's for those people who don't have the resources to go out and build their own data centers, but still they want to have some amount of control of data, or whatever reasons they may have in house. Okay, so that is the forms of cloud today, and cloud offers new ways to access computing capacity and data quickly and inexpensively. So that is something quite obvious. Then DevOps, Internet of Things, artificial intelligence, blah, 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 all the buzzwords, they rely on the scalability, efficiency, and ubiquity of cloud. So can you imagine something like GPT-3 coming into existence without the power of that much compute that cloud provides? So 2018, there was a huge number of money earned by the cloud industry. 2022, a lot more money is going to be made. That's pretty cool, and I'm not going to get into the numbers much, but to us, mainly, it saves time, money, and you don't really need to worry about the physical, aspects of a computer like uptimes, hardware failure, so on and so forth. That's handled by your service provider. And for students, we can sign up for a free trial. 1 year, we can abuse the service, to our will, and we can deploy apps, train models, carry out projects, and so much, much more. Okay, so that's all great, but what exactly is cloud? That's a pretty good question. So some of you might say, okay, is it a supercomputer? Uh, well, personally, I don't think it's a supercomputer because that's more focused on the compute. Uh, Others might say it's a mainframe computer, and that also is not exactly the case because, as I'll explain, servers over here stacked together in racks is what makes up cloud. So a mainframe would be something like a huge amount of RAM and CPU. It's just one big computer. So what exactly is cloud? So the best way, I guess, to explain it is a lot of storage situated close to a high compute capacity. Okay, so this is done because in the next slide I've randomly Google searched and found that it's 1.145 exabytes of data is generated per day. All right, so that amount of data moving it through networks or like even locally, it's not a joke. So it's quite difficult to do so, and instead of moving it around, you bring the compute and the processing closer to where the data is. So that in essence is what cloud is. And over here you can see a single site cloud or a data center that I've been harping about for the past 5 minutes. You can see each of these. There's no pointer. Okay, great. So each of these boxes would be a server which contains CPU, RAM, hard drives, and so on and so forth. And each of these stacked together, and they can be put into a rack. Now, a rack is nothing but like a bunch of servers interconnected using a network switch. So these are all connected using the switch, and multiple racks can then be connected using aggregate switches. And then these switches can then be connected to core switches, which let the data center be connected to the internet. So it's just a bunch of servers in racks, and then multiple racks connected to each other. Pretty simple. So this is a single data center. Like if you have done the quick labs, you might see them keep talking about zones like US Central 1A, B, C. So your A, B, and C is each of them will be one such data center. And then you have US East, West, so on. And multiple data centers interconnected is going to be known as geographically distributed cloud. All right. So, okay. So, what does this exactly bring to the game? So, what is the benefit of doing all of this? It's mainly availability and scale. So, you can easily scale cloud. You can just add more servers, more racks as and when. You can handle large amounts of data because that's what the aim of cloud is. It makes compute way more affordable, and because of this new power, you have now capabilities of creating new programming paradigms such as MapReduce, parallel programming models, so on and so forth. So it's pretty handy. And yeah, basically, cloud summed up as a meme is stonks. Okay, coming back, you might be saying, all right, I don't really care about scaling and stuff. How do I care? All you care about is on-demand access. And yes, that's right. You said the words on-demand access. Typically, when you go to a store and you want to buy a computer or something, you'll be like, okay, fine, I want this hardware. If you go to The cloud store, though, okay, there's no actual cloud store, it's GCP, but stick with this example. If you do go to this cloud store and the clerk or whatever guy comes up to you and says, okay, what do you want? Let me walk you through the options that this guy will give you. So option one, he's like, this is the latest, best in class hardware as a service. He's trying to sell you this product. So hardware as a service is nothing but these racks and servers. They will rent them out as is. They won't install any software. It's just the hardware. So you might say, why not just go and buy a computer? Well, you could do that, or you could rent it out and they will take care of the wiring. They will take care of the electricity bill. They will take care of the hardware problems and everything, right? And you can just focus on creating your own infrastructure and building up above that. And the good is that you have absolute control. The bad is that you need expertise to set up and manage whatever you are deploying. I mean, you can't just say, okay, fine, let me make without knowing what you're doing, you can't really make another GCP competitor, can you? So that's a downfall. And security issues, any software you install, the security issues caused by that software, that's your headache. You'll say then, okay, I don't really know how to make, handle all these servers, manually and install, a virtualized environment on it. So the guy is like, the store clerk is like, okay, I got you. I have another option. It's called infrastructure as a service. Now this provides you all the benefits of hardware as a service, having to not deal with all the physical stuff, as well as flexible, scalable compute and storage. So it achieves this by providing you, they provide you their own custom virtualized environment. Now, all of this sounds complicated. I promise I'll get to this in a bit, like if you stick to the cloud engineering track. Okay, so this also allows you to create a lot of virtual topologies. So you have virtual networks and virtual, machines that you can create. So what are the cons? Usually, your virtual environment is created on a bunch of hardware, right? Obviously. So this hardware can actually support multiple such environments. So you can have multiple people using your hardware. And in some cases, if you're running something like that's very security sensitive, then this might not be the best idea. But then again, it depends on your use case. So depending on what do you say, this platform like GCP or AWS, you can only control as much as what they let you control, right? Obviously. So that's another downfall. Like you can't tweak the amount of power your compute uses. I don't know why you would want to do that, but that's a thing you won't be able to. So in case you've fallen asleep, please wake up. This is a wake up call. Thanks. Carrying on. You're like, okay, fine. I don't know about all this virtual instance and all. All I want is I want to run Apache web server. I want to run a website and I want people to be able to access my website. So this guy is like, okay, don't worry. That's all chill. We'll make the virtual machines for you. And since we are controlling the virtual machine creation and all, we can sprinkle a few extra features since we control it, such as load balancing, monitoring, and so on and so forth, to help your application really thrive. So that's amazing. This means you can just plonk your software stuff, and as long as it runs in the VM, you have access to all the features. Amazing. The problem is, of course, you now can't create the VMs on your own, right? And like you did in infrastructure as a service, now it's all in their hands. And all this monitoring stuff they're sprinkling and what do you say, other features they're providing, right? Now you're completely reliant on a service like Google App Engine or Beanstalk if you talk about Amazon. So it's like kind of how you get sucked into the Apple ecosystem. It's difficult to move to Android. Same thing. Okay, so the next thing is software as a service. So I have created this in Google Slides, right? And believe it or not, it's an example of software as a service. The entirety of Google Slides is running off a platform as a service thing that Google has built in the backend. So you and me using Google Drive or search or anything, These are all examples of where cloud is being leveraged. So can you just imagine the kind of scale where cloud is used in our daily lives? I can't. Uh, that's, I think, an exercise left for you. But it's pretty mind blowing if you think of it that way. And okay, back to software as a service. Pros is you get software in a controlled environment, all right, like Google Docs. Bad thing is that you're stuck in Google Docs, so you can only do things that you can do there. And as an example, I'll let you guess what the example is. So that's it. I guess that's the end of the intro session for cloud. I hope you found it interesting. Please stay on if you're interested in the cloud engineering track. If you're more interested in the data science track or ML track, there's a banner flashing, I guess, sometime now. I can't see it because I'm sharing my screen. So there's a banner flashing with the link, or in the description or the chat box. You can find these links and you can go ahead and go there. Don't worry if what you say you want to watch both of them. We'll record these sessions and we'll what do you say upload them to our YouTube channel. So we're gonna wait for about 2-3 minutes for depending on how you guys want to go. Thank you. Okay, so we'll be continuing with the cloud engineering track around 6:21. So you guys can take a rest break. I'll look at the questions that you guys have and all right, 6:21. Let's get back. That was a short break. Okay, so I have been, talking about how cloud is amazing and stuff. And as a follow-up, I mentioned virtualized environments and virtual machines, instances. So what really are they, and how do you make one? Virtual machines, I guess, are the heart of cloud. And lucky for you, on my new cooking show, Cooking with Pranav, I shall be teaching you how to make a virtual machine today. 5 to 10 minute cooking time, served hot, do not consume, and that image is not representative of how a VM looks. So let's get on with it. Any good, recipe starts off with a base, right? So this is our base. You have your physical hardware, your CPU, RAM, hard drives, the usual stuff. And you have installed your operating system on this physical hardware. You can see it as this halo floating around above this representation of a computer, and you have your applications running on this operating system. So this is pretty standard, pretty cool. I guess most this is intuitive enough. And now for the special ingredient, we add the hypervisor. So you might be asking, of course, you would be asking, what is a hypervisor? So coming back to this diagram, the operating system controls your hardware, your CPU, RAM, and disk. And when an application with appropriate permissions asks for resources, let's say you launch Chrome and it needs 2 GB of RAM just to launch, right? The operating system will then see if it's a legit request, and it will provide it according to how much is available. So that's a very dumbed down version, but it should do the trick. Similarly, the hypervisor also controls your physical hardware, just like your operating system. You install this hypervisor on your physical hardware, just like the operating system. But the only difference is it will now take your hardware and it will split it up into virtual hardware. So let's say, for example, you have a CPU with 4 cores. The hypervisor, depending on whatever you input or whatever it needs to do, it can split up these 4 cores into 2 cores each, and it can provide it as an interface such that it provides virtual hardware with just 2 cores. So now any operating system being installed or running will see this as a 2 core system, and it'll be like, oh, okay, I'm running on hardware with 2 cores. So the OS thinks it's running on actual hardware, whereas it's just the hypervisor splitting up the actual hardware into virtual hardware. So that's a lot of hardware talk. That's basically it. That's all it does. So it passes the calls, and it handles all the conversion from virtual to physical and stuff. And that's it. You have yourself a virtual machine now. And this entire stack over here, this diagram, I guess it is a little misrepresented, but this entire stack over here constitutes a virtual machine. So you might be saying, okay, cool. That's a pretty good definition you explained there. But I have Oracle VirtualBox, right? And I run that on Windows or Linux. And how is that possible? So what I just explained here is called a type 1 hypervisor, where you install the hypervisor like as you would a normal operating system. What you guys are probably used to is called a type 2 hypervisor, which is basically, it basically works the same, except you install a hypervisor, Oracle VirtualBox, onto your operating system as an application. Then this application slash hypervisor will request your OS for 2 cores or 3 cores or whatever you've set your virtual machines to. And then it will provide those resources to these virtual machines over here. And that's it. Done. You've learned what a virtual machine is and how it's made. So now you might be asking yourself, why do we even need virtual machines, right? So first off, the thing is, it will provide amazing isolation, right? I won't get into how. That's beyond the scope of this talk, but it provides amazing isolation. Secondly, for as an end user, I'll give you a very common scenario, right? So you have all these applications here. This is assuming you have a system with just an operating system, just Windows or just Linux. None of that hypervisor do that. Okay, this is just plain on vanilla what we're used to. So let's say we want to run what do you say, Apache web server, which requires just humor me for a bit. Let's say it takes Python 3.6, and then you also have an instance of MySQL running, which say it runs Python 3.8. So MySQL needs Python 3.8, Apache Web Server needs 3.6, and these are obviously two different Pythons. You can try to jumble them and try to juggle them and make it work, but this is just two applications. Remember, Now you can have many such applications. It's not uncommon to see 5 to 6 applications running at once to keep your web apps running. So all of them will have their own dependencies, their own library requirements, and trying to manage all of this causes something called a dependency matrix hell. So of course, all these apps can cause conflicts. So how does a virtual machine solve this? Well, it might seem a little inefficient at face value, which you're absolutely correct about, but you can run each app in its own virtual machine. So it can have its own dependencies installed in this, guest operating system, which is what you call, operating systems running within a virtual machine. So it can have its own dependencies, everything, isolated in its own nice little box over here. And each app can be running on the same hardware, as you can see, but independently. So that's pretty cool. And as I alluded to before, there is a tiny problem, which is in fact a quite large problem that arises because of this. And that is that running an OS is no joke. It takes up a lot of resources, and it will probably fry your computer. I mean, have you tried running 4 virtual machines of Ubuntu on your system at once? Yeah, I don't think you've dared to do that at all. But so you get the point, right? So running an operating system just to run a particular app, it doesn't really make sense. It uses too many resources. Each time you have to set up a virtual machine, so the setup is complex. Then you obviously have this entire overhead. So all that performance is being used up running this operating system. So is there a solution? Well, of course, this is where containers comes in, and it's this magical little thing that I'll get into in a minute. I will be specifically talking about Docker because that's the most what do you say widespread container or system in use. So okay, before getting into Docker, I need to explain briefly what a container is. So at the heart of every operating system is something known as a kernel. So there might be different names depending on an operating system, but this kernel is basically the part that provides the basic functionality. You can, as an analogy, you can think of like regardless of the version of C you use or which OS you are running that C program in, you will always find printf in C, right? If you're using the standard library. So similarly, as a part of a kernel, you will always find some basic, I could say building blocks or interfaces that your programs can talk to. And Docker, rather containers, take advantage of this, where each container will assume that all it has is that one basic building block. This allows any application to run on using just that slice. So all of these applications will assume they are running off that basic those basic building blocks. So this they're getting their own share of operating system. So over here, I explained that uh, let me just go to this diagram. Yeah. So over here, the hardware is the thing that's being virtualized. Whereas, now in containers, you are in fact virtualizing the operating system. So you're giving a slice to each container. Now, you might be asking, okay, fine, but how do applications exactly work, right? Do you just install them like an exe? No, it's quite different than that, actually. So, like I said, the operating system provides a base layer, right? So you can think of this sort of like an onion with this kernel at the core. Okay, and let's say you want to install that same Zulip app, for example, which needs Python 3.6. So if you want a Zulip container, Zulip server container, then what you would do is you would first take that container, that core kernel layer. On top of that, you would add the layer for GCC because Python needs GCC to compile certain libraries, right? So on top of that GCC layer, after installing that, you add the layer for Python 3.6, and then you add the layer for your Zulip server app, right? So you see, Zulip needed Python 3.6, which needed GCC, which needs some kernel level commands. So that's how your container image is built with all these layers. And let's say another app over here, again, humor me, MySQL requires Python 3.8. All right. So now instead of rebuilding your entire onion layer image thing, you can just replace that Python 3.6 layer with Python 3.8, and voila, you have another container which can run. So this is amazing in the sense that now you can run only one operating system, and as long as I'll come to what this Docker thing is, and as long as you have this container image system, you can now run multiple apps independently with isolation. So what is this Docker thing? So this is what. So in Docker, you have this thing called a Docker engine, but the general concept is known as a container runtime. What a container runtime does is, first off, it manages the creation of all these containers, and how much resource how much resource each container will get, right? Secondly, all these, that you might have an image with Redis, or again MySQL server, and things like that. So it keeps let's say a store of all images and locally, and it helps you manage all of this. So now coming to specifically to Docker, you can see it's an application built on this entire concept that I just explained to you. So you can see the client where you can run command line arguments saying Docker build, pull, run. I'll come to all of this when we do the lab. And you also have this Docker host, which is the heart. And you over here, like I said, you have all those container images. So you might have an Ubuntu image. So this Ubuntu image is basically built up for multiple layers until you reach the layer where Ubuntu can actually run. This is Redis. And then using the Docker daemon, you can then use an image and create, a container running this image, right? And you can create so many of them depending. This registry over here that you see, you can think of it as GitHub for these Docker images. So one key thing is that, like I mentioned, you have that base kernel, right? So when you create an image and let's say it runs on a particular using this Docker runtime, then you can be confident that you can take this image and literally run it on any other system where Docker can be installed. So that is another amazing thing. You don't have to worry about, oh, I don't, the specs don't meet up and all. You can control that, in fact, but the library dependency, all of it is neatly packaged into this image, like I've mentioned. So these will run literally anywhere where you can install Docker. So one last concept before getting to the lab is the concept of networking. So some of you, if you are experienced with what do you say, VirtualBox networking, you might recognize this. But anyway, I'll get into it. So let's say you are running two containers within the Docker environment. All right. So it doesn't matter what they're running, but let's say they need network connectivity. So these containers then are, of course, Docker handles the connection of these containers to the outer world. It does this through creating a virtual network device, a virtual bridge, and these containers will be connected to it again virtually. Now, this virtual bridge is then further connected to your physical network card. Okay, this again managed by Docker, and then of course it can talk to the outer world. One of the most important things is that a container can communicate with the things that are on the internet. However, things on the internet cannot directly communicate with a container. This would be similar to the concept you might have learned in like as NAT, right? If you've heard of NAT, this is quite similar to that. All right, so I've been harping about Docker and stuff for good 36 minutes. So we'll quickly get to the lab. I'll be just going through this. If you want, you can follow along, but I would suggest that you would let all of this sink in. I'll start the lab, and you could again, like I said, follow me along, or you could let it all sink in. Just watch me run the commands, and run parallel to what's happening over here. So yeah, I'm just going to wait for that to spawn. Prerequisites, open the GCP console. All of this, if you have done Quick Labs, you should be quite familiar with. So the first thing that we need to do is to open up Cloud Shell and to run Docker Hello World. So I might face an issue. So I'll just share my entire screen rather than getting to. Okay, great. It's visible. Okay, cool. So I'm going to open a new private window. On tab, this sign in. So again, if you're feeling a little left behind and all, no worries. You can just rewind and watch again at your own pace. Or even if you miss it completely, we are always going to upload the recording, so you can watch it whenever you want. This is mainly to tie in all this jargon I've been speaking about and actually show you what it does. Hopefully this happens quickly. All right, so Cloud Shell. All right, so let's get back to this. Okay, so now the thing is, like I said, right, you have, what do you say, images, correct? So when you say Docker run, okay, uh, this image over here is called the hello world image. It's supposed to, output hello world. So what you will see is when I run it, right? Okay, let me just increase the font size. No, never mind. All right, so good enough. So yeah, you can see that over here, it said it can't find it locally. So it pulls it from the Docker repository. So this is one of the default, what do you say, paths given. So it's able to pull it from that online repository or registry here, and it's able to deploy a container. And as you saw, the what do you say? It just what do you say? Outputs hello from Docker, and then it just messages. It just gives some default strings. All right. Okay. What's the next step? The next step is to basically take a list. Yeah, this is how you list your images. So you can see it now. You locally have hello world as an image. All right. Moving on. I'm going to rush through this because we're slightly running out of time. So again, if I run it now, you don't get that what do you say? Not present local message because it's present locally. So now let's look at the containers that are running. So I just ran this container and it output whatever command. So the way Docker images are built is that they follow through, and whatever command they have in or whatever you've configured to, they'll run it and they'll exit after that. So of course it has exited after outputting hello, and it has there's nothing running, and this will show you all the things that you had run. All right, so this is your history. Okay, let's go next. Now let us make that Docker image, with all the layers and stuff. So this example is for a Node.js app, and this is just creating. I'll just copy paste this. This is just a boilerplate code, and okay, so over here, I'll just tell you a few basic things. So you are again referring to an official Node runtime as parent image. So this is Node.js. They in the registry would have their own image. So this is how you're referring to that. And this is the work directory add expose. I will come to all of this. So, okay, basically the work directory tells it that you are limited to this directory and you cannot exit out of it. So if you notice, this is /app, right? So you cannot exit to just the root directory, right? And this will then add what do you say, the contents of that directory into the container, and it can only access what was present locally. So, okay, let me explain that again. Over here, you have something, locally. All right. So this sets the working directory, and this will add the content to /app in your container. So now, when you do expose 80, if you remember, I spoke about the networking, right? So in this container, you are exposing the port 80. All right. So now you're running some startup commands, and this EOF is just a cat instruction. So okay, carrying on. So we're going to be constructing another file called app.js, which contains the actual server code. And now we shall build the image. So this dot, of course, if you're used to Linux, it means the current directory. So the app name is, again, okay, let me just quickly authorize this. The app name is called Node App 1, and this is the tag we're providing. So you can think of it as version 0.1 that we are giving as a label. So the name is called Node App 1, what we have named it. And okay, let's wait. Now, if we, list the images, you should see this. Okay, I'm just going to skip this command as well. This is pretty obvious. If you run Docker images, you'll see that our node app with the tag, aka version number that you have given, is going to be given. This image ID is actually a SHA-1 hash or SHA-256. I'm so sorry, I can't really remember, but it's just a fraction of that, and it is a unique identifier for that image. Okay, so okay, let's get back. I think it should be done. So we can see that let me just increase this. Yeah, so we can see over here Node app appears successfully. So let us now run this. Now this command is quite a mouthful, so I'll just tell you what exactly it does. So over here, we're running our our Node app 01 version. What do you call it? Container image, and we are creating the container my app. Okay, and over here, if you remember, I told you that you cannot access containers from the outer world, right? Like the internet, you can't access it directly. So Docker, what it provides is through this through its networking. I won't really say this network bridge, but through its networking, it will let you similar to an old command. If a connection from what we have set here from port 4000, if there is an incoming connection to port 4000, it will then forward it to our container that we have run over here. So an example, let me just quickly get back, would be, I'm really sorry, give me a second. Yeah. So if we do curl, right, I need to open another thing, because if I do control C over here, it'll shut down the container as well. So if I do curl, I get this message, hello world, right? So you're able to access it from the outside world, port 4000. Then Docker internally is mapping this 4000 to the 80 that we ran in that expose command in the, yeah, over here when we said expose. So it's exposing it, and we are able to access the thing. So now let us control C. It exited, and now we've stopped my app and we have removed my app. All right. So we can do log, we can do cd test. All right. So let's we can edit this application as well. So okay, that's okay. We're already in C test. Never mind. So okay, replace hello world with another string. Okay, so let's go to nano hello world.js. Okay, no, that's not it. App.js. I'm so sorry. I have .js. All right, and let's quickly just replace it with just world. I'm a bit lazy and short on time, so I don't care. Um, okay, and okay, there we go. We've modified it. Now, if you remember, we had built an image with that as the directory, right? So now we have to rebuild that image so that the change is reflected. And here you see over here. Remember, I spoke about the layers, right? So the node 6 already is present. You don't need to re-download node, and then again, it's caching all the other files in app, and all it is doing is it is what do you say, this modified file, that is where the change is being reflected. So you can see the onion layering sort of thing really working out here. This of course has the benefit that you don't need to rebuild the entire app from scratch. So that's pretty cool. And let's run it. And this time we are exposing it to port 8080 instead of 80. All right, let's run it. And yeah, that's pretty much it. Give me a second. Now we can, what do you say, test the containers. So see, it outputs world as demonstrated. So, okay, first container we made, I think it's still running. Oh God, it's not running anymore. But basically you should be able to, what do you say, get that again. If I hadn't done Control C, I would have got that output. So, okay, what's the last thing? Debug, right? I'm not going to cover much of this. This, I think, is fairly, what do you say, self-explanatory. So, over here, what we are doing is, remember this registry that I was talking about? Well, you don't need to necessarily use the registry provided by Docker. Just like GitHub versus GitLabs, Google has its own, what do you say, registry, and you can gcr.io, that's what it's called. And we can then configure it. And for the sake of this app, I'm not really going to explain too much. This is self-explanatory, and I'll just okay, never mind. I'm not gonna complete this. This is all pretty much same. You're pushing it over here, your Docker image. So instead of git push, you're doing Docker push because it's a Docker image, remember. Then you can navigate, you can remove all your containers, and uh, you can then also remove the child images. So remember, node app dependent on node, right? So it'll remove all of these, and then in the end, you'll have no images left locally. And then you can again, as if nothing happened, you can pull it from. So if you remember, initially we pulled hello world from, we just added hello world, and it knew because it was in the default, what do you say, registry. Now we are specifying a manual address to pull the thing from. It's similar to clone from, what do you say, Git, or pull from Git also. And then you're running it. And then you get the welcome to cloud message that we modified. And if I check my progress, it's going to fail because I did none of this. But thank you so much for sticking. Please leave any questions you have in, what do you say, the Slack channel or the comments. I'll check it out. Now, Bhargav will be explaining Kubernetes, and I shall, end this lab. And thank you so much for sticking. Right. So.
Okay, hello guys. I'm Bhargav. I'm going to be starting off with Kubernetes. Before we actually get into Kubernetes, I just want to get through why you'd want to use Kubernetes. So, what Kubernetes essentially does is it helps you run these said containers and Docker containers out in the real world. But before we get to why you would actually even use Kubernetes, let's understand why it's necessary. So we saw that Docker efficiently runs these containers and it does so really well. So you notice that if you probably want, say, an app server in one container, another DB in another container and say another binary. Docker does that very, very well. It'll let you run these and it'll help with the communication between these containers too. So what's the necessity of getting another such framework or orchestration software to run containers? The main reason for that is Docker won't really function well in a production environment. To understand what a production environment, these are two common terms: a development environment and a production environment. A development environment is probably where you and your team you're the only guys accessing the app that is deployed or whatever. It's just the team working on it, checking stuff out, testing, so on and so forth. A production environment is where it's actually put out to the open world and you have your actual clients using them, using your services or your website, whatever it is you put out. So the issue with Docker is it is not ready for a production environment. Even if you put it on one huge compute server, it has a lot of issues with it. It cannot really scale these kind of containers as such. And with lots of traffics coming in, containers will fail and close. And if it closes, it's not necessary that it'll always restart and be brought back up. So in short, Docker is not production ready. So that's essentially why you would want to use Kubernetes. So what is Kubernetes? Well, it's an open source container orchestration system for blah, 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 blah. So essentially what it means is you can deploy containerized apps, you can scale them, you can manage them. And Kubernetes does all of this for you in a simplistic and easy method. So this is normally a workflow you would take if you create an application. You would convert your one huge monolithic application into microservices. This was again like the previous slide where you had one DB, one front end, one web server, so on. And this you would containerize each of these things using Docker, and you would deploy these using Kubernetes. So how do we actually deploy using Kubernetes? We'll get to that in the next slide. So as said, you just running a barebone container inside a node or a VM isn't really production ready. It has a lot of issues with it, and it is bound to crash. So the Kubernetes solution is something called a pod. So what exactly is a pod? If you look at this cluster image right here, it represents a cluster. So what a cluster essentially is it's a bunch of computers running together. And in each of these computers, you can deploy these things called pods. So what a pod essentially is, it has containers running within them. That's it. That's all there is to it. You can have one or more containers in a pod. So for a more refined diagram, you can look at this representation below. So this hexagon is a pod. Within that, you have a container running. And within the container, you have your app, which is the cube here, and the circle is the container. So this is essentially what a pod is. You can just bring these up as many as you want, and you can put normally one container into one pod. That is normally the best practice. And then just put these pods into your Kubernetes cluster, and it'll run. Another feature of pods is you can put them on any node. It doesn't matter where you put them. It will, as long as it's on the cluster, it will work. So perfect, that pretty much solves the issue, right? Not really. So there are a few issues with pods too. You can't really just use bare pods and deploy them out into a production environment. The major issues with these are, well, much like a Docker container, like how it can access the outside internet, but the outside internet cannot access the container unless you specify some sort of port mapping. You have a similar thing with pods too. Like the pod can communicate with the outside world, like it can send requests, download data, so on and so forth. But if it's hosting a website, the outside internet cannot access that website. It has no way of actually reaching out into the pod or reaching the pod at all. Another issue with pods is you can't really scale pods. So if you have, say, one pod running a website and you get lots of traffic in, and you'd probably need much more pods to handle that sort of traffic, it won't scale easily. You'll have to manually bring them up. And that honestly is a pain. So that's one more issue. And finally, it's updating pods is a little bit of a hassle too. So say you have another web server maybe running which is at version 1, it runs on port 80. And say you update the web server to another version that runs on port 443. Changing the pod or updating these port mappings and the version in the pod is not easy. It is not going to happen as you'd expect it to. The only way you could actually change it is kill the previous pod and bring up the newer one. So as you could see, running bare pods actually has a lot of issues. So let's actually tackle them one by one. The first one would be how do we handle the networking issue, the issue of the pod not being, the outside world not being able to talk to the pod. So how this is done is using a Kubernetes object called a service. So what exactly is a service? It's just, you can think of it as something that provides networking capabilities. There are multiple types of services, load balancers, node ports, and cluster IPs. For simplicity, I'm just going to talk about load balancers because it's the easiest to understand. So what you would do is this image right here, this is a load balancer. You map it to one pod, like you attach it to one pod, and this allows this pod to be accessed by the outside internet. So this blue dotted line as such is your Kubernetes cluster. So if in case someone from the outside internet hits this IP of the pod, of the load balancer, the load balancer will actually redirect it to the pod and send the request back to the internet. So this allows outside traffic to be routed into the pod. Then the immediate question you'd get is, do I need one load balancer per pod? What if I have, say, multiple instances running the same thing? Can't I just use one load balancer? And to that, absolutely, you can. Like I said, you can either map one load balancer to a pod, that's your choice, or you could use a Kubernetes feature called labels. So what this is essentially each pod has a label attached to it. So it's like you're putting a sticker on a pod saying, okay, you have this label and you identify by this label. So in this case, the label is app:/db. You can keep this as to any key value pair. It doesn't really matter. It could be absolutely anything you want. So here, what you can, and then you can tell this load balancer, any request you get, reroute to one of the pods that have a label app:/db. So this load balancer gets traffic from the outside internet, and it will reroute it to these said pods which have that label. And like usual, it will go to this pod, goes to the container, a request comes back out, sends it to the user. Fairly simple. So this 100% solves the networking issue. So now, what about the other one? What about scaling and what about updates? How do we handle this? A fairly simple and straightforward solution is to use deployments. This again is another sort of Kubernetes object. So what this does is, say you just tell a deployment what pod to run and how many of them to run for. So you can tell, okay, deployment, I need 3 instances of front end. And the deployment will take care of that. It'll say, okay, I'm supposed to bring up 3 instances of front end. I'll bring them up. I have currently so-and-so running. I need to match 3 replicas. And it'll bring them up. So this, and the other features of deployments are, if in case you want to update the software in the front end, you can do so. This deployment will detect those kind of changes, close the older pods, and bring up the new ones almost instantaneously. It's extremely fast and it's extremely useful in production scenarios. Apart from that, it also health checks and maintains your pods. So if in case, say, one of these pods gets overwhelmed and it just dies out, it crashes, the deployment will notice that, say, okay, this thing crashed. I have only 1 running, whereas I needed 2 running. It will bring up another one automatically. So it maintains the health of your cluster. It also helps updates, and it's the full-fledged scenario. It provides everything you'd need. So that's what a deployment is. And then these are perfect for production environments. They're production ready. Okay, so to compare the 3 units, we have a container. This runs a required image. It does so perfectly. Issues are it could crash, and this crash can affect the rest of the application. So if when you deploy this thing into a Kubernetes environment, okay, you try with the pod. It can run one or more containers. You can run as many pods as you want. And you can run them on a Kubernetes cluster instead of a local machine. But then again, issues are the networking, and it isn't really flexible to modifications. So to handle the issues of a pod, again, you use a deployment. This in turn runs one or more pods. And then this again does everything for you. It handles health checks, verifies stability, and it's also again flexible to modification. So this is everything you need out of deploying to a production environment. So that's essentially it. We've covered containers, pods, services. Services, like I said, is essentially just like a load balancer or anything that provides networking capabilities, and deployments. So to actually show these to you in real time, I'll probably work this out in the lab. The lab I will be using is orchestrating the cloud with Kubernetes. I'm going to quite blaze through this lab, but what I'm going to do is everything we do, I'm going to visualize it for you. I'm just going to use diagrams and show it to you. So let's just get started with this. Oh no. Oof. Okay, I've run this lab quite a few times. Okay, that's all right. I'll just show you the commands and I'll visualize how they run. So again, boilerplate setup. All right, first thing we do with Kubernetes is to set the compute zone. This specifies where you want your cluster to run. And that's essentially it. It sets the compute/zone. So here it's US Central 1B. And then this is the command to create a cluster. You can run this in your Cloud Shell. This essentially just creates a cluster called IO. It actually brings up three machines. So what this command would do is this. If this gray box is your Kubernetes cluster, it brings up 3 VMs. That's it for your Kubernetes cluster to use. That's what this command does. Then next, we copy the sample code, which we're going to use here to deploy pods, services, and a few deployments. And this would be the first thing we deploy. We're just going to deploy a normal Nginx server. We use the image Nginx. So this would be the command kubectl create deployment Nginx and the image. So what kubectl does is it's actually a command line tool which helps you interact with your cluster. So it's it'll be installed in your cloud console, I mean your cloud shell, and you can just use it to communicate with your entire Kubernetes cluster. So what kubectl create deployment does is it first creates a deployment, and then immediately after we expose this deployment using a load balancer. So like I said, if you create a deployment or a pod, you can't directly just access it. You have to make it open to the outside world. So we do so using this load balancer. So what this does essentially is this. It creates a deployment. This deployment creates a pod which runs the Nginx image. And then we created that one service which creates a load balancer, and it maps to the deployment. We directly told expose deployment. So it goes like, okay, I see this deployment, I'm going to expose this. And this this allows the outside internet to actually access this Nginx web server. So I think the next thing would be to actually just look at the web server. Yeah, if you tried this, you'd be able to see the default Nginx web page. And that's essentially your first task. That will finish the first task entirely. Then moving on, we get into pods. Some definitions about pods. Here's a YAML configuration about a pod. This actually creates the pod entirely. So this is boilerplate API version kind and pod. This is to specify which pool of objects to pick, and the kind specifies the object to actually pick. Then metadata, as it says, you specify a name for the pod and whatever labels you want to. If you remember, I told you can use services to search for instances or pods using labels. This is exactly that. And then for the specs, you can specify whichever containers to run. Currently, this is running this monolith app, and it has a few port mappings. So that's essentially just the pod. And this is the command to create the pod. Essentially, all Kubernetes commands you'll see will be of this format: kubectl create -f and the file. -f is just to point at the file you want to use. So you'll normally have a bunch of these configuration files, which are all .yaml files, and feeding this file to kubectl will actually bring it up in the cluster. So once you create this pod, it first makes the pod monolith. And to actually interact with this pod, we have this hack called port forward. So what this does, I'll just visualize this too. What it did was initially we created that one pod called monolith, and that's running this monolith application for us. We then created this weird hacky thing called a port forwarding. So what this does is it does not let the outside world connect to your pod, but it lets you connect to your pod using your using your Cloud Shell. So essentially, what it's doing is it's creating a port mapping between your Cloud Shell machine and this pod. So like I said, it's just a simple hack to check if this thing is up and running. So after that's running, we're just going to be checking. We're going to hit a few different endpoints on that pod, just the normal homepage /secure/login, get a few stuff in, and then with /login, you'll actually get a token which you're going to use later. This is to ensure secure login. Then you can send that credentials to secure, and you'll be able to log in again, so on and so forth. Then you have this thing called kubectl logs. This literally, as the name suggests, it feeds you the names of the logs that come out. So it will show you all sorts of logs that come out of the pod or whichever is generated by the pod, errors, just warnings, messages, everything. -f is to just see it in real time. Then kubectl exec works pretty much like Docker exec. What it does is it just runs this command on the pod, on the container exactly, and in this case, it's just a shell. It's /bin/sh. So it'll put you into the container and it'll return the shell. So you can just start running stuff in the pod. It's especially useful when you're debugging. So what that would do is from your Cloud Console, you literally end up inside this container. You'll be in this container with shell access, and you can look around the pod, modify files, check what's going wrong, so on, and it's very helpful for debugging. Then we move on to services. So like I said, services are of 3 types: cluster IPs, node ports, and load balancer. I think in this lab we'll be using node ports too, along with load balancers. We've already used load balancers once. So we'll be using node port 2 if I'm right. So yeah, here we're going to first create this thing called one pod called secure monolith. Then a bunch of secrets to store the TLS certificate, so on. This, you don't really have to go in depth here. Essentially, what you'll need to realize is we create this pod called secure monolith, and we create a service for this pod called monolith.yaml. And this is essentially a node port. How a node port is different from a load balancer is node port binds to exactly one pod, and it has 3 ports actually. One is the port to serve on the pod, that is 443. The target port is what internal container should use to access that pod, and the node port is the port outside users should use to access that pod. That might be a little confusing, but key thing to note here is this works specifically on just one pod, unlike a load balancer. To notice here, we have the selector. It looks for pods with app equal to monolith and secure equal to enabled. So once we create this, it looks sort of like that. It created that one pod and it created a service. But the tricky thing here is if you try to access that pod by hitting that service, this is just creating a firewall rule. Yeah, when you try to access that pod on that service, it times out. It does not actually work. The reason why it does not work is this service looks for 2 labels. One is the app equal to monolith and app equal to, sorry, and what is, I think secure equal to enabled. It looks for these 2 labels. But whereas that pod only had app equal to monolith. So since it didn't find the other label, this pod did not match its description. So it did not reroute to here. It just dropped the packets. So what we got to do now is for this pod, add that extra label that says secure equal to enable, so that this service will actually go a reroute to this pod. So that it looks sort of like this in the end. How that's done is it's very simple. You just you create kubectl label. This will label the pods with whatever label you put. It already had app equal to monolith. So now you need the new one that says secure equal to enabled. So if you kubectl label the pod, the name of the pod you want to label with so, it'll label it for you. So at that point, this pod will have the both monolith and secure equal to enabled label in there. And hence the load balancer will reroute traffic to the pod. So that's essentially with the pods and services. The last thing we'll be doing is working with deployments. So here, what we're going to do is we're going to have three deployments essentially. One is the auth, another is hello, and another is front end. So what these do, these create three separate services. Three separate containers, and you're going to create three separate services to access these containers too. You can see the descriptions of these services and pods you're going to run through the YAML files that are provided. It essentially runs these images, and it has these port mappings, yada, yada, yada. And then again, as usual, kubectl create the name of the file. Kubectl create the name of the file. So you're going to do this 3 times. One is for auth, deployment auth, service for auth, deployment for hello, service for hello, and deployment for front end and a service for front end. Once you've actually brought those up, again, a deployment does everything for you, right? So it brings up the pod, checks its health, makes sure everything's running fine, so on and everything. So it creates 3 deployments. One is auth, one is front end, one is hello, and it binds these services to each of these. Like I said, you can either create one service for each deployment as you'd want, or you could create just one thing and say, okay, map to all of these deployments. You can do that too. You just have to specify the labels to look for, and that will work just as well. In this case, these are 3 separate things, and they actually need their own services. So you're creating 3 different services. And once that's done, I think you just have to hit that external IP using curl, and you'll get a hello response, and that's it. That should be the entirety of your lab. That will be all. I'm so sorry that I couldn't run it. I think I've run this lab quite a few times just to test this out. I think that'll be all for this session. If you have any sort of doubts, just please put them on to the comments. I'll try to look into them now, or maybe later, or through Slack. Thank you. That's it from my side.
Thank you, Bhargav. I guess this is the end of our event then. We hope you guys liked it. And we have a lot more events planned for the near future. So stay tuned for that. Thank you, guys. Bye-bye.